Okay, we're going to go ahead and get started. Yesterday, we had some different things up here, and one of them was a cathode ray tube. And we said that most of the particles traveled straight through from the cathode to the anode, but if we applied a charge below and above, then we had a deflection of that particle. Go ahead. So, like I said yesterday, we talked about the Thomson cathode ray tube experiment. We had some experiments up here we did that kind of showed what that would look like. And these are actually particles that are traveling through, and they're negatively charged. Okay, and the reason why they know they're negatively charged is because the charges they put below and above electrically caused it to push to one side, or I guess pull to one side, depending upon how you want to state that. And so any opposites attract, and so that's why it maneuvered upwards, because the positive attracted those particles. So it wasn't light. It looks like light, but it's not. So I think I had you put two things down. Did I have put a third thing down?
No, not third.
Why don't you put that third thing down that I remembered later on, that because the atom is neutral, because like when we do isotopes, you guys know that if it has so many protons, then you can equal it number of electrons, right? Mm-hmm. And we know that the atom's neutral, so if it has these negative particles...
What's that last word? In matter.
In matter. If it has negative particles, then that means something has to counteract that negative charge. And it has to be something positive that does that. So they started looking for this positive particle. It's kind of like if you know something has one thing, there might be something else that counteracts that, and then so now you have something else to look for. And that's what they had, something else to look for. And that's when we get into Rutherford's experiment. So these atoms are made up of negative particles. Why? Well, it was affected by negative and positive charge, where it was attracted to the positive and repelled by the negative. And we all know that a basic understanding of physical science is that opposites attract in charges. So then the electrons have a mass, and then we had that little wheel. And then if it was light, that wheel wouldn't move. But we know that there was something that had a mass that was hitting that wheel that caused it to go across. So there was another reason. They knew that this all matter, because what they used is this metal was all different types of metal. So this metal here was all different types. And the particles were the exact same thing, how they were affected no matter what metal was used. And there must be positive particles in this metal that is yet to be discovered or kind of found out about. So then we get to Rutherford's experiment, and I'm not sure how much you have of that. Did we just have the one going straight through, or did we have some of the other deflections?
We had deflection. We had the deflection. We went right at the end.
Okay, so at the beginning, these are helium particles, and they're plus charged. And so what they're doing, these particles have a mass, and they're also positive. So most of them go straight through, like 99.99%, or just a huge amount. And we could tell because this fluorescent screen was really brightening up directly parallel to the source. But every once in a while you would have another portion light up. But very, very few. And so they were able to do some things. First of all, what do you think caused the deflection?
The gold foil.
Yeah, something in the gold foil, but the gold foil is there for all the other ones. The the 999 that go through, but the 1 out of 1,000 that may deflect, what's causing that deflection? Right, I mean, we call it an isotope in atom, but what in the atom do you think is causing that deflection? If this is positively charged, what do we know about what's deflecting it?
Negative.
The positive charge.
Yeah,
Because likes repel.
yeah.
So as it's going through, there is something that's causing it to move away from its normal path. And so it's being deflected, and the thought was, since this is positive, there must be something in the gold foil that's positive, and that's what they were kind of looking for, that was going to deflect it. And even some of them deflected to the point where they were just amazed that it was deflected backwards off the gold foil. And they said it was kind of like shooting a bullet through paper and it bouncing back. Like you target shooting and then all of a sudden the bullet comes back at you. That'd be scary. Okay? But also this object that's in there, what do we know about that object that's doing the deflection? What's its size going to be like? So the object in here is causing deflection. What do you think its size is like? Really, 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 really small. They found out that this piece of gold foil was about 10,000 atoms thick later on when they got more information and they did measurement. But so there's 10,000 atoms back to back within this piece of gold foil. That even shows it's even more very, very small. And it also shows that the piece of gold foil is mostly empty space. So we see three things, that there's something positive in the gold foil, it's deflecting it. What's that called now? What do we call the positive thing in the atom that proton? Okay? And we know that the atom is mostly empty space, okay? Because there's a big gap between what we call the nucleus and the electrons. Okay? We know the nucleus is extremely small, but it is densely packed together. So I've got 3 statements on this slide that I'd like you to write down. So Rutherford's experiment showed that the atom is mostly empty space. You guys are mostly empty space. Did you guys know that? No. Now you can find... My teacher told me today I'm just empty space. That wouldn't be good to say to your parents. Right? I'd be getting calls. Why are you calling my son or daughter empty space? I don't think that's very nice. Okay? and sometimes they might agree with me. Right?
Just my brain.
Empty space. We're mostly empty space, so it's kind of funny. It's like, well, if we're mostly empty space, why doesn't my hand pass through my other hand? Because both of them are mostly empty space, right? Now that'd be cool if you could do that and it just goes right through. Okay? Right? Wouldn't it be? Is this empty space? Atoms are empty space, right?
Yeah, I mean the table's really nothing.
Right. So you're writing with nothing. You're writing on nothing.
You are nothing. You're nothing.
I told them that, but they're going to go home and say, Mr. Garland said, we're just empty space.
Well, that's their parents.
We are.
So, there's something else. So, we know like charges repel. Guess what's coming together when I put my hands together? What's not allowing my hands to go through one another? What's on the outside of an atom? What's outside? Electrons. So electrons coming close to electrons, what are they eventually going to do? Repel. Repel. Okay? And that's the same with the nucleus. The nucleus is made up of protons, and other atoms' nucleus is made of protons, so they're not going to be able to get close together either. They're going to repel. Alright? Something in the atom has a positive charge. Well, we kind of know why that is because we have deflection. Number 3, we also know that wherever this positive charge is, it's in a center that is really densely packed. And so the analogy would be if you put a golf ball in the middle of Tom Osborne Field in Nebraska, at War Memorial. And then the upper stands, the circumference of the upper stands would be where the electrons are located. So we're talking about a golf ball in the center, 50-yard line. And then where the electrons would be the outer portion, and the rest of that is empty. The rest of that space is empty. There's nothing. It's kind of like our solar system. When you think about our solar system, there's just not a whole lot of matter within our solar system when you look at the space between the planets. I mean, we're wanting to go to Mars, or eventually the thought is gain enough technology and enough knowledge to safely send somebody there. First thing they're going to try to do, and by 2024, is to send mission to the moon again, and then from there gain information to maybe be able to send somebody to Mars. And so our solar system is really a lot of space, because that traveling time, you're going through a lot of empty space.
Wait, so if your hand's empty space, what about the bones?
Yep. And all matter's empty space. All matter's a lot of empty space, but the reason why, there's some other reasons why that we can see things and they have that appearance. Okay, number 3. Okay, you guys got that? And then the fourth one, number 4 is the nucleus is extremely small. We had very few deflections. If it was bigger, we'd have more deflections. We just don't. Okay? Now, this flows right into talking about the atomic structure or the structure of the atom and what kind it looks like. And so I'm going to do a simple drawing. It's much more complex than the model I'm going to show you, but the model that I'm going to show you is what we kind of look at and think of the atom. It's just a model. A model has certain constraints that creates why it's not perfect. Okay? So one of the constraints is I can't draw this outer portion big enough to represent the proportion of the atom. So inside the atom, we have a nucleus. So I'm going to do hydrogen or helium's atom. Okay? That's what I'm going to show is helium's atom.
How do we draw that?
It's up to you.
Are we going to need different colors like you?
No. No, I'm just doing it for your benefit, so you can see it.
So we don't have to draw it.
Okay? No, I want you to draw it. You guys have great imaginations. You can probably figure a way to differentiate between the red, the black, and the blue. Okay? So, you use that imagination to do that. Okay. This is helium. Okay? Helium is 4, 2. So this is the isotope for helium. And the 4 represents this center. So the 4 represents this center. This center is extremely small. Okay, I could put probably just a dot with a circle, and that wouldn't even show it to the scale it would be. So this is not very good scale-wise. But we do see a lot of empty space here.
Imagine if you saw it.
So everything outside that nucleus is empty space. We know that the parts in here are positive. We have 2 positive ones. The red ones are neutral. That would be the neutrons. We haven't talked about discovery of neutrons, but they kind of come later. They figured out they figured out these atoms when they looked at the protons and their mass. When they looked at the atoms, they showed it having a bigger mass than what they thought it would be. And that's because there's another particle in there called a neutron. On the outside, we have electrons. Okay? So we're going to give some information about electrons here. So, electrons. What are some characteristics you know about electrons?
Negatively charged.
Okay, so they have a negative charge. All right, what else?
They like waffles.
Okay, they have a tiny mass. Okay, they are equal and opposite the charge of a proton. That's why they can cancel them out. So they're extremely small. They have little mass, but they're mighty in charge. They're opposite. They're equal. They're about 1/2000th the mass of a proton. So think of it. They have 1/2000th the mass of a proton, but they're equal and opposite charge. Okay, extremely high charge to its mass when you look at the ratio. Okay, electrons can be lost and gained by the atom. Okay, and they're on the outside of the nucleus, located outside the nucleus. Okay? So, when you guys are asked on the test on Tuesday to give information to describe the atomic structure of the atom, and all you put down is the atom has protons, neutrons, and electrons. There's a lot more to say about those subatomic particles that make it up. Electrons have a negative charge. They have a tiny mass compared to protons. They're equal and opposite of the protons. They can be lost and gained. That's what we call reactivity. When they start to get reactive, it's because they lose and gain electrons. And they're located on the outside of the nucleus. A lot of times we call it an electron cloud when we look at it. Okay? Second thing we want to take a look at is the protons. So we're going to look at protons next. So protons. What do we know about protons? Positive charge. Okay, what else? Where are they located? Okay, located in the middle. We call that the nucleus. Okay, are they lost and gained by the atom? No, never lost and gained. They never move their home bodies. They never move. Okay? So, the protons are stationary. Stationary just is a simple way of saying that they're not going to move. They're not going to be lost or gained. Okay? They help make up the mass of the atom. Okay, and they give the atom its identity. And I'm running out of space here, so I'm going to put it up here. Okay, the protons are what give the atom its physical characteristics. That's why copper is copper color, or reddish-brown color, because the protons are what give it those characteristics. So if you look at the characteristics of a particular atom, it's because of the protons. The chemical characteristics a lot of times is because of the electrons. Okay? The last one doesn't have a lot of fanfare, and it's the nucleus. And the nucleus, not the nucleus, the neutron. What do we know about the neutron? Which we haven't talked much about.
No charge.
No charge.
No charge.
Isn't that what the bartender said to the neutron? For you, no charge. Right? Okay? So you want to be a neutron's buddy because every time you go in a bar or a place like that, you get free drinks, right? Because no charge.
We should have a science joke Monday.
Okay, we'll start it this Monday. Think of a science joke.
Science joke Monday.
Okay, you guys saw that one up there, right?
Yeah.
Yeah.
Okay.
Where?
Okay,
It's alright, you can't see it.
located in the nucleus.
I can't see. They're all gone.
And they help make up the mass of the atom.
Because all the good ones.
Okay? And they also help hold the nucleus together. Now, you get to thinking, if you got 2 or 3 individuals that just really hate each other, they don't want to be in the same spot, sometimes there has to be somebody that would be present in which to be at least civil to one another. The neutrons are those individuals that say the protons, what do we know about protons? They're all positive. We get a bunch of positives together, what do they want to do? What do positives want to do?
Go away from
Repel? So how in the heck do they all stay together, all in that small area in the nucleus? It's called a nuclear force, and the neutrons contribute to that process of holding them together. All right? So there's a lot of information there. This is called atomic structure. It's taking a look at the atom in a way of these subatomic particles. Okay? And you'll have to, I guarantee you, there'll be a question. It'll be 5 or 6 points. And it seems like I always have students that will not study essay questions. And so on the last portion of the test, there'll be like 9 or 10 points out of 60 or 65. That'll be essay. And they will miss the essay because they don't take the time to study it. This is not that hard. Okay? Protons, positive charge, located in the nucleus. They don't move. They help make up the mass of the atom. Electrons are located outside. They're very tiny in mass in comparison. They're equal and opposite, though, in charge, which means they have equal amounts of both. Have to balance out the charge. They're lost and gained by the atom, and then, of course, we got neutrons. Okay, and then the structure and how it's put together. All right.